Okay, next speaker is Goldhaber-Gordon from Stanford, and the title of his talk is Ferromagnetism near three-quarters filling or in twisted bilayer graphene. Yeah.
So, so it's good to be able to get together with this group of people on this occasion that's both sad but also inspiring. We've heard a lot about Shoucheng and what he's meant to the field and to many of us. I'd like to say something that we've heard before, but maybe give my own take on it, which is that to me, fundamentally, Shoucheng was a visionary. He saw the world as it ought to be, simple and elegant, and I think that I was lulled early on into feeling that his vision had nothing to do with the actual world, because I had seen his 4D quantum Hall effect, and we heard beautifully from Zhang how, in fact, the themes of that showed up over and over. But Shoucheng was so excited about suggesting experimental ideas that I ended up a bit over a decade ago really getting into topological insulators because of his enthusiasm. And what I'm talking about today, I only barely got to tell Shoucheng about the beginnings of it before he passed away, but it's a set of ideas and ways of thinking that I never would have come to without Shoucheng. And as I go through, I'll also allude to some of my other work that he played a role in. So, before I go on, let me just say that besides Shoucheng, there are many people who helped with this work, gave inspiration, a number of theorists who are really important in my thinking, and I would say among them really chiefly Alan MacDonald and co-workers, but also Senthil and Steve Kivelson and Oscar Vafek, so a number of people who are here. And this work is mostly work done by my group in collaboration with Mark Kastner. Some of the work that I'll speak about briefly makes use of magnetic topological insulators, chalcogenide-based materials that were grown by Kang Wang's group at UCLA. And also, we use boron nitride that comes from Watanabe and Taniguchi in Japan, who are, I think, the most cited condensed matter researchers now in the world. All right, so what are the ideas here? I think that probably all of you have heard about moire systems and twisted bilayer graphene. I'll give you my own view about what's exciting about these areas. But if you take two lattices and you twist them slightly with respect to each other, then they beat against each other and form a superlattice, a so-called moire or basket weave pattern. And that's true in real space. It's also true in momentum space. And because in graphene, the low energy states are at the corners of the Brillouin zone, those, rather than at low momentum, those get twisted in momentum space and moved separately and moved apart from each other. So if you have two layers of graphene twisted by an angle, then you have two Dirac cones that are separated in momentum space. Now that's the first approximation, but in fact these two layers interact with each other. So you're going to open up a gap where the cones cross, and as you make the angle of twist smaller and smaller and move these points closer in momentum space, you can see that this gap will move towards zero energy and the band will get flatter and flatter, and maybe at some point you should eventually get a band that is completely flat, which nearly a decade ago a number of theorists suggested, and Alan MacDonald's group was, as you heard in his talk earlier, instrumental in getting people to think about this. So, why is this interesting? So this so-called flat band, so really what I've tried to show is that at the magic angle, at some special angle, the velocity of this cone should go to zero, but in fact, more detailed calculations show that you should get a very flat band that even in fact should be separated from dispersing bands. So why is a flat band interesting? I think many of you have come to this from the context of quantum Hall effect, where we remove the effect of kinetic energy. All the electrons have the same kinetic energy if they're all within a Landau level. And now, if you have a partially filled Landau level, then Coulomb interactions direct how electrons organize themselves. And so this is sort of the same picture, but without a magnetic field. Instead, kinetic energy is removed from the picture by just having a band where all these different momentum states effectively have the same energy. So this was expected at some level to give rise to interesting behaviors because you can get almost any arrangement of electrons if interactions are important. Still, I think that few people anticipated how exciting this would be, but just over a year ago, Pablo Herrero's group announced that they had not only achieved something that seemed like it was a flat band system in twisted bilayer graphene, but that the system had a correlated insulating state when you had 2 electrons per moire cell, which is what they called half filling because you can fill 4 electrons per moire cell. And they also showed, even more strikingly, that there was superconductivity when you went near to that point. So that got many people, including me and my group, excited, and we worked to follow up on this. And here's just an example of another beautiful piece of work on this from Matt Yankowitz and Corey Dean and Andrea Young, showing that there are interesting states not only at charge degeneracy and at complete empty band or filled band, but also at half filled and maybe also 3/4 filled band. So that if you you have these degenerate states, spin and valley indices, and even if you do not completely fill the degenerate states, you seem to get correlated insulating states. All right, so these samples, for those of you who are not immersed in this, these samples are kind of neat in how they're made. We make a sticky stamp, and we pick up atomically thin materials, and then pick up another material and another material to make a stack. These were techniques that were largely developed at Columbia. And then there's some magic here, which is that you can define an edge of this sample by etching and then evaporate a metal over it. And remarkably, even though this graphene sticks out from the cladding layers, the boron nitride that protects it from the outside world, by only maybe a nanometer, nonetheless you get really reliable, robust electrical contact. So that's magic, but it's not magic that only works in New York. It's translation invariant, and so we use it. So here's a micrograph of the device I'll mostly talk about that's a few microns in size, and that has the structure of a Hall bar, so we can drive current, measure voltages longitudinally and transverse, and we can gate it from top and bottom, so we can control density and the electric field normal to the plane. So here I'm showing you the resistance, the longitudinal resistance as a function of top gate voltage and back gate voltage. And so you can think cutting it from bottom left to top right, we're changing the density, we're changing the 2 gates in the same direction. And this is the charge neutrality point. This is 4 electrons per moire cell, or what Pablo called full filling. This is 0 electrons per moire cell. Going from top left to bottom right, we're changing the electric field normal to the plane. You can see it doesn't do anything as dramatic as the changing the density, but it also does something. We aimed for near to the magic angle of around 1.1 degrees, and you can see we were targeting 1.17 degrees, and we ended up with 1.20 degrees, and this is now typical for how well we can do it. So we can get to maybe a 1/30th of a degree of the angle that we're trying to hit. So let's look a little bit more closely. It turns out that our sample, in terms of its physics, looks rather different from what people had seen before, and we think we have a sense of why it is. And that is that one of the two layers of boron nitride, which you can think of just as an atomically flat insulator for most purposes, but one of the two layers of boron nitride that clad the twisted bilayer is almost perfectly aligned with the neighboring layer of graphene. So the twist is less than 1 degree between the boron nitride and the graphene, and I'll explain why I think that's important. But so consider two devices, one with the aligned boron nitride, the other with intentionally misaligned boron nitride, somewhat similar twist angle for the graphene. We can plot these same kinds of plots that I showed you of longitudinal resistance versus density and field normal to the plane. Now I've rotated them or transformed them so that density is the horizontal axis and displacement field is the vertical axis. And at this scale, these look kind of similar. You may already notice that displacement field seems to do something a bit different in this case where one of the boron nitrides is aligned. That is, positive and negative displacement field don't do exactly the same thing, and that probably reflects the asymmetry in the vertical direction. But let's do, I like to say that color plots can cover a multitude of sins. Let's do line cuts to really see what's happening here. So let's do a cut of density at a particular displacement field. So if we do this for the non-aligned case, we see that the charge neutrality point, we have a resistance per square of around 1 kiloohm. And this is characteristic, 1 to 5 kiloohms is characteristic for good, clean graphene. And in fact, you should never get more than 20 kiloohms, because 20 kiloohms corresponds to 4e squared over pi h. And if you don't have localization, which you shouldn't have in graphene, you should never have more resistance than 20 kiloohms. And yet, if we look at this sample, you see that we have about 100 kiloohms per square, which is not true of any of the other reported twisted bilayer samples. So that's a striking difference. And in fact, there's precedent for this. There's one other feature I wanted to point out, which is that here I've shown you the peaks associated with complete filling of all the states and complete emptying of all of the states in the band. Sorry, this one's complete emptying. And if you go a little bit beyond complete filling or a little bit beyond complete emptying, there are other features that appear to be associated with 1 electron per graphene boron nitride moire. So the period of the graphene boron nitride moire is almost the same as the period of the graphene moire. It's about 6% off. All right, so there is precedent for seeing this high resistance at the charge neutrality point with alignment of boron nitride. I just wanted to show you, looking back, we did not intend to align the graphene with boron nitride, but if we look at, an image of the sample and we look at the facet of the boron nitride flake and the facet of the graphene flake, and we move these on top of each other in the computer, we can see that they're about 1 degree off from each other, and indeed the transport backs that up. So there's precedent for seeing high resistance at the charge neutrality point when there's alignment with boron nitride. Both my group and Pablo Murillo Herrera's group saw about 6 years ago that you could get very high resistance at the charge neutrality point when aligned with boron nitride if the graphene was really clean. And in fact, we got up to megohms of resistance at the charge neutrality point. Pablo's group emphasized that there was a gap that was around room temperature. We focused on the very low temperature behavior where the resistance is no longer activated but still goes up very high. And so what seems to be happening in the band structure is that there's a gap opened around the charge neutrality point, obviously not a very hard gap. All right, so to visualize this, we sort of played with looking at these lattices and seeing how they fit on top of each other. So I'm going to lay together the 3 nearly aligned lattices, and you can see that we get a moire pattern when we put 2 on top of each other, and then when we put the 3rd on top of each other, where we know all of these angles. You can see it again it looks not only is the period almost the same, but actually the orientation of the two moires is about the same. So, so it's kind of interesting. Maybe it even matters that, that the two moires are approximately the same period and or aligned, or maybe it just matters that we open up a gap because of alignment to the boron nitride. We don't know yet. So, all right, so what did we see in this sample? So first of all, we didn't see superconductivity, and my student Aaron Sharp, who had made this sample and was studying it, decided nonetheless to carefully look at its transport properties. And he started by just trying to measure what was the density as a function of gate voltage. So he looked at the Hall effect as a function of small magnetic fields for different gate voltages, and I'm plotting it now in terms of carrier density. This is in Pablo's terms, where 1 is 4 electrons per unit cell, per moire cell. So this is half an electron per moire cell. This is 2 electrons per moire cell. So you can see there's a Hall slope, and it changes a bit as you're going across, and that allows us to calibrate how much effect the gate voltage has. Here's 2.5 electrons per moire cell. And then at 3 electrons per moire cell, something looks different. So there's a very strong slope of the Hall signal. At very low fields, it gets up to kiloohms at very low fields. And so that was really striking. And so Aaron decided to study this more carefully. This was done at 1.5 Kelvin in a cryostat that wasn't very carefully filtered, or wasn't filtered at all. And so Aaron decided to cool this down in a dilution refrigerator, and something even more dramatic happened, which was now this anomalous Hall effect becomes, it's not only having a sharp behavior near zero magnetic field, but it's hysteretic. So we sweep the magnetic field, and we can switch, apparently, a magnetic state. And the size of this signal is kiloohms, and it's primarily in the Hall signal. There's also a small effect in the longitudinal signal that we think is just a matter of mixing of the Hall signal. Interestingly, so this is again at 3/4 filling. Interestingly, this is at 2 Kelvin. So it turned out we didn't need to be colder. We just needed to have a quieter electromagnetic environment, better filtering. So now Aaron mapped out what happened as he changed the density. And on the left axis, I'm showing the size of the anomalous Hall signal, half the size of this jump, basically. And you can see it reaches its maximum very near 3/4 filling, or 3 electrons per moire cell. The other plot is of the Hall slope away from zero magnetic field. And you can see that that starts out looking electron-like on the left side, hole-like on the right side, and it's tending toward low-density holes, low-density electrons. And then in the middle, they don't diverge because presumably there are puddles associated with a small band gap insulator or semi-metal, and it's there where this looks like there's a gap where we get this large anomalous Hall signal. So this is a very reproducible behavior, so we can go around our hysteresis loop many times, and you can see even the fine features are reproduced. It looks like there's probably domain structure that is consistent from one sweep to the next, and therefore we get jumps at the same set of coercive fields. We don't, by the way, fully understand what's going on near zero. It's likely some kind of magnetocaloric effect, but we haven't studied that much. So the signal also shows up in longitudinal resistance in funny ways. It's even non-monotonic there. But again, I think that that's primarily mixing in of something that's fundamentally a Hall signal, probably because of the domain structure. So this is a very stable effect. So we can wait over a period of hours, and the Hall signal doesn't change at zero field. And so you can see that here's a hysteresis loop that we did before the sweep, and then we stay at zero field, and then we continue on this hysteresis loop, and it just continues the same way that it was. So this is a kind of unfortunate plot that the Hall signal was nearly zero here, but that's primarily because there was some mixing of the longitudinal resistance. You can see that it was nearly zero, but it was actually on the top curve of this hysteresis loop. So we can look at it as a function of temperature and see that at low temperature there's a big hysteresis loop, we need to go to relatively large fields, over 50 millitesla to switch it. And then as we raise the temperature, that goes down. Also, the size of the anomalous Hall signal goes down. We can plot both of those. And you can see that the size of the anomalous Hall signal is almost flat out to 3 Kelvin and then starts going down. It actually, if you look carefully, even gets bigger as we raise the temperature. Maybe it's easier to align domains. The coercive field goes steadily down as we go to temperature, and these die at 4 or 5 Kelvin. So this is not a millikelvin behavior. It's pretty robust, though it's not a room temperature magnet, but for someone for whom 4 Kelvin is swelteringly hot, this is pretty impressive. And actually, I'll maybe at the end, in honor of Shoucheng, come back to what this may be good for. So the Hall signal can be really large. If you look at the size of change from positive to negative, it corresponds to 10.5 kiloohms, plus minus 10.5 kiloohms. So this is getting up toward h over e squared. No, certainly, we would not claim that this is quantized, and I'll get into this more, but it's really starting to smell like something that could have topological behavior that could give you this large signal. All right, so just for comparison, I've been working for about 6 years, 5-6 years on magnetic topological insulators, and Eli Fox, who's in the audience, who is the other student in my group who was very actively involved in the twisted bilayer graphene work, also did beautiful work on the chrome-doped bismuth antimony telluride system. There we lithographically make structures, and this is a system that Shoucheng convinced me to work on. I felt it was a terribly dirty system. It is a terribly dirty system. It's miraculous that it works as well as it does, but after some years working on it, we do seem to get behavior that's primarily due to the chiral edge modes and insulating bulk at 0 magnetic field, where time reversal symmetry is broken by magnetization, not by an external field. And so ideally, you'd get longitudinal resistivity of 0 and Hall resistivity of h over e squared, 25,812 point something ohms. Indeed, this works really quite well. In 2013, Qikun Shui's group demonstrated that within a few percent, the system showed quantized Hall resistance, although there was still very substantial on order h over e squared longitudinal resistance. In the time since then, work by my group, Moses Chan and Jagadish Mudera, and recently Lawrence Molenkamp's group has really pushed how good the quantization is. So our recent results are at about 2 parts in 10 million. So and Lawrence Molenkamp's are comparable. So we're getting to the point that, and that's on vanadium doped instead of chrome doped material that we used. So this is getting up toward where the quantization that's used in quantum Hall effect is, and I think this is possibly the most likely application of these materials in the near term, that they may be used for metrology, where if we can push up the temperature scales a bit, you can make a quantum Hall resistance standard that doesn't require a magnetic field. Our work was in collaboration with the National Institute of Standards and Technologies, and metrologists are quite interested in this. So I showed you sort of intermediate, not the latest results, but this development really occurred quite rapidly over a period of 6 years, from not having quantization to getting quite strong quantization. And if we look at where we are in twisted bilayer graphene, we're nowhere near quantization. The longitudinal resistivity is 6 kiloohms or so, so it's nowhere near 0. The Hall resistivity is nowhere near h over e squared. It's a little bit less than half of that. We could look at, and in fact, we don't even seem to see a minimum in longitudinal resistivity near 3/4 filling. But if instead we plot the conductivity, then we do actually get a minimum. And I would say that the sort of data that we're getting, they're heading toward perhaps towards something that might look like it has Chern number 2, but I would say the quality of the data are comparable to where, say, Joe Czekelsky and Takura were in 2012, shortly before quantization was achieved in these, or close to quantization was achieved in the chalcogenides. So, all right, we don't know what's happening here, but one simple picture is that this degenerate band is breaking into bands that are polarized according to their spin and valley, and we're filling 3 of these, but not filling the 4th, and therefore we get something with a net Chern number. This is an idea that's been suggested by a number of theorists, including Oscar and Allen, and we had quite active discussions with them. This is only the simplest picture for what might be happening. There are also some calculations that suggest a gap should be opened in this system where we align with boron nitride. If people are interested, I can talk about non-local measurements that we've made that give some insights into the edge state conduction. There are still many possibilities for what the possible state of the system is, including, since we don't really see an insulator, it could be something that's valley polarized, but Senthil has suggested that it could be something like 2 copies of a composite fermion, nu equals a half state, and then there are ideas for non-coplanar spin order that could also give orbital order. So I just want to give you one sense of the latest stuff on this that's not posted on arXiv yet. You might ask, what's the order? And to try to understand that, we might look at the in-plane versus out-of-plane magnetic field. We designed a rotator in collaboration with AutoCube, a company, and therefore we can put magnetic field in any direction. And we've gone, all the way from perpendicular magnetic field to nearly in the plane, where the in-plane field is 10 times the out-of-plane field. If we plot the transport behavior as a function of just the out-of-plane field, then you can see that the curves almost collapse at the low field part, and it seems really what matters is the out-of-plane field. So that suggests, as we already suspected, that orbital order is really the key here, but we still don't know what kind it is. So just to summarize, there is this remarkable behavior of magnetism that we didn't expect in twisted bilayer graphene at 3 electrons per moire cell. It's likely that the boron nitride alignment is important. The size of the anomalous Hall effect is really large, larger to my knowledge than anything that's been seen for non-topological systems, and the Hall angle is pretty big. We see evidence that I skipped over for edge conduction. I also didn't show that we can flip the magnetism with a small DC current. And then just to circle back to Shoucheng, the fact that we can flip the magnetism with a small DC current suggests that you could make a memory out of this. And you might say, well, that's pretty ridiculous. Why would you want a memory that works only at a few Kelvin? But in fact, that's exactly what's needed for interfacing with a quantum computer. A quantum computer needs a classical computer to control it and read it out. And right now, there's a lot of investment in putting a processor close to a quantum computer and much less in putting memory. The lowest power switching for memory, for reasonably fast memory today, is so-called spin-orbit torque memory, which is based on magnetism. And it turns out that this system, we require a current density that is 4 orders of magnitude lower, suggesting we might get a power that is 100 million times lower per switch than the state of the art of spin orbit torque. So I think that's, if you call that an application, then I think that would have warmed Shoucheng's heart. Thank you.
Question?
Yes, thank you for a nice talk. So I just look at the hysteresis of the quantum anomalous Hall. I see a very obvious asymmetric behavior. So you see the amplitude of anomalous Hall is, Hall resistance is about 2 times bigger in the positive field side than in the negative side. Do you have some understanding why is that?
Yes, so she was asking, what's giving rise to this asymmetry in the size of the anomalous Hall signal here and here. I think it's primarily mixing with the longitudinal resistance. That is, this is not a homogeneous system. These systems have twist angle variation. We have evidence that in the multiple switches and other things that form domains, which mean that the bulk is not totally insulating. So we're probably getting mixing of longitudinal and Hall. I think there's a subtler asymmetry in this curve where we have a certain direction in the plane, and actually it may matter one direction versus the other. But for out of plane, I think it's pretty much the mixing.
Okay, so there are two questions actually. First question is, how are you sure that you are ordering? So you're interpreting the system in momentum space, but how are you sure that your moire pattern is regular enough? And this is not really the physics that happening is not in real space. And the second question is, because the reason why I'm asking, because these sort of multiple steps remind very much what happens in the Josephson junction arrays, where you have little islands of superconductor. Yes. And you have sort of trapped flux that is here and there, and you have multiple steps which really reminiscent of this physics.
Yes. So the question is, should we most properly be thinking of this in momentum space or in real space? We know there's disorder. Maybe we're getting sort of clusters that are forming. So I would say I'm not very wedded to the momentum space picture. I think that it's the simplest description. Let's say it's at least a counterweight to Pablo calling what he sees a Mott insulator, and I think there's no evidence that it's a real space picture. But fundamentally, we don't. I'm just giving you the simplest picture and saying there are many other possibilities. I'd love to talk about it. In terms of the role of disorder, we think probably the most important disorder is twist angle disorder based on comparisons to other systems, but even the small amount of charge disorder so that the filling is not the same everywhere may also be important.
So in your graph explanation of the Chern number,
yeah,
all the Chern numbers you're getting are 1, and as far as I know, that's the only thing you can get from these type of simple ferromagnetic, you break up lambda levels.
Yeah.
But you say
yes,
you've got Chern number 2. So what's the connection?
Yes. So Andre pointed out something that I sort of left hanging. It seems like this semicircle might be headed toward 0 longitudinal conductance and -2 for the Hall conductance, which would correspond to Chern number 2. And indeed, we never see more than 10.5 kiloohms. So that's less than 13 kiloohms. So it would be, at least we haven't proven that if there's a Chern number, it must be 1. I agree with you that the simplest theoretical pictures would give you Chern number 1. I'm at this point agnostic about whether it's Chern number 1, whether it's Chern number 2, or maybe it's not even a Chern insulator at all. But I think the possibilities, at least we're trying to narrow them down.
In the bismuth telluride quantum analysis system, there's a 0 Hall plateau in sigma xy. So do you see any features of 0 plateau here? So
the question was about a 0 plateau. So there, you're talking about the axion insulator sort of state. So in the chrome-doped bismuth antimony telluride, in certain circumstances, it's possible to get the magnetism in the top layer and in the bottom layer opposite. Here, it's not clear that that's possible. There aren't two well-separated layers. So the short answer is no, we don't see a 0 plateau, but I'd be excited if you have ideas for where to see it.
Yeah. So in another moire system, like twisted double bilayer graphene here.
Yes.
Yeah. Right. Right. So in Philip Kim's data, actually, he shows that when you turn on Inplane field, actually, the system become more and more insulating. I just wonder, do you see similar things here, or, how the system respond to an Inplane magnetic field?
All right, so the question is about an in-plane magnetic field, and Shenko was asking, does the system become more and more insulating? We did apply a large in-plane field. Maybe I can ask Eli, are you on? Yes, so we're trying to figure it out. I don't think it was as dramatic as was seen in that other work, Shenko. Yeah.
David, for non-experts in the twisted bilayer graphene, so is it the same regime where they saw superconductivity before, the same doping range, and the only thing that the substrate is now sort of oriented the same way as?
So excellent question. So Eugene was asking where, can I orient where we are relative to where people have looked at twisted bilayer graphene before? I'm sorry for not being so good at navigating this. All right, so here we are. So the correlated insulator that Pablo's group discovered is at 2 electrons per moire cell, or what they called half filling. And just a little bit away from there, there's some controversy over whether in a clean enough system you only see 1 dome or 2 domes, but just below and just above half filling are where you see superconductivity. We are instead at 3/4 filling. So it's the same general ratio. It's not far away, but it's a different filling. Yeah, and we don't see this this hysteretic behavior at any of the other fillings.
The last question.
In Pablo and Corey and Andrea's data, they see Landau fans emanating at various fillings. Do you see any of that?
So what do we see for Landau fans? The answer is yes, we do see them, and particularly around 3/4, the nu equals 1 state is pretty prominent, which may suggest that it's connected to a Chern insulator, but I think I can show you offline what it looks like. Yeah.
Okay, so because of the time limit, so we probably just stop here. And if you have more questions, you can ask later. And with that, I think we will conclude this section. Let's thank our speaker again.